This is the last one from the revision quiz 1. It is number 11, and it says a system consists of two subsystems A and B with independent failure times arranged as shown. So it's a parallel system, and it's given us an exponential, is that A and B are exponential failure times, and the failure time A has a mean 8.2 and the failure time of B has a mean 1.8. And it says find the mean time to failure of the system. So you might be tempted to do the same thing that we did 2 videos ago in number 9, which is almost the same as this one, but not quite. In that one we were given our lambda values straight away. In this one we're given mean time to failure. So the first thing to note is that for an exponential system, only for exponential systems, you get the mean time to failure is 1 over lambda. Exponential. Whoa. Exponential systems. So in this case we've been given the mean time to failure, so we know the lambda value implicitly for each of A and B systems because they're exponential and we're given the mean times to failure. So that's pretty straightforward. So how do we actually work out the mean time to failure for the system? Well, recall that the mean time to failure for any system is actually given by the integral from 0 to infinity of the reliability function. And that's the system reliability function with respect to time. So we could go through this whole thing again, but I'm not going to. If you've forgotten how to get this, then have a look at the answer I just did for question number 9. For two side-by-side or two parallel exponential systems, this turns out to be the same thing every time, and so this expression for the mean times to failure is actually equal to e to the minus lambda a plus e to the minus lambda b minus e to the minus, in open brackets, lambda a plus lambda b t dt. So this is the expression for the reliability of two parallel exponential systems. And as I say, if you've forgotten how to get to that point, then I suggest you go and have a look at the video for number 9. So what do we do from here? So we probably don't need to yet substitute in our values because we can do a little bit more of this integration directly. So let's just take the integrals for each one of these components. So for this, we get we want to be able to bring that out, the lambda a in front. So we're going to get minus 1 over lambda a e to the minus lambda a t. Forgot all my t's. Minus lambda a t, and then this is going to be minus 1 over lambda b e to the minus lambda bt, and then this is going to be plus 1 over lambda a plus lambda b e to the minus lambda a plus lambda b t. And this is all going to be from infinity to, from 0 to infinity. So can we get further than that? I think we can. This is going to be actually relatively straightforward to figure out if you think about it, because we've got the two extremes of infinity and 0. So firstly, let's take this whole expression substituting in infinity for t. So what is this term? We got some sort of constant times e to the minus a constant times infinity. So anytime we've got e to the minus infinity, that's going to go to 0, and we're going to get 0, and then we got minus, and then we've got the same thing again, so that's going to be 0, and then plus, we've got a constant, e to the minus a constant times infinity, so that's going to be 0 again. So we get 0 minus 0, or minus 0 plus 0, and that whole thing is 0. Then in the next round, we want to take 0 and substitute that in for t right throughout this whole expression. So this time, what happens to the exponential component of each of these. Well, this time it goes to 1, because e to the minus 0 is just 1. So all of the e's go to 1, and we end up with minus 1 over lambda a, and then we get minus 1 over lambda b, and we get plus 1 over lambda a plus lambda b. So remembering that we've got a minus sign out the front here, if we want to get rid of all this, we can just make that plus, that's going to be minus, and we end up with the mean time to failure for this system, and I'm going to bring it up to the top. The mean time to failure for this system is going to be equal to 1 over lambda a, hold on a second. No, that's right. 1 over lambda a plus 1 over lambda b minus 1 over lambda a plus lambda b. And I think that's kind of neat. So let's just chuck these numbers into the calculator. We've got lambda a is, well, this expression here is actually given to us. We're given the mean time to failure A, which is 8.2. This one is the mean time to failure of B, so 1.8. This one's not so easy, so we're actually going to have 1 over the mean time to failures. So 1 over this sum of the reciprocals of the mean time to failure. So I think that's kind of an interesting solution, that the mean time to failure of the system is equal to the sum of the mean times to failure minus 1 over the sum of the reciprocals of the mean time to failure, or 1 over the sum of the lambda values. So I hope that makes sense. So this is going to be equal to 8.2 plus 1.8 plus 1 over 1 on 8.2 plus 1 on 1.8. That's really ugly. Let's do that again. See if I can write that a bit neater. So this whole thing is equal to 8.2 plus 1.8 plus 1 over 1 on 8.2 plus 1 on 1.8, and that is equal to 8.2 plus 1.8 plus 1 divided by 8.2 plus 1 divided by 1.8. It gives us 11, no, got it wrong. 8.2 plus 1.8, so it's 10 minus, I'll put in a plus there instead of a minus, 1 divided by 8.2 plus 1 divided by 1.8. That gives us 8.524. And that is the answer. So it's kind of a fiddly thing to get all the way to the end. If you wanted to remember that, you probably could, although it's highly likely you might forget it. But see if you can work through all those steps, and I think you'll see it's relatively straightforward to go through. First, determine the reliability of the system, then take the integral of the reliability of the system from 0 to infinity, and that works out to be quite a nice little function of the sum of the two mean times to failure of each of the subcomponents minus 1 divided by the the sum of the lambda functions, or 1 divided by the sum of the reciprocals of the mean times to failure of the components. Hope that makes sense. Happy to explain further if required.